It's a great pleasure to welcome Min to speak in this seminar. He's by no means a stranger to this audience and this setting, because he, until a few years back, was a student in Maryland, and upon successfully completing his studies and getting a PhD degree, Min spent some time as a postdoc in Princeton with Emmanuel Abe, and then joined Tsinghua-Berkeley University in Shenzhen, China, where he is now a faculty member. And Min also went to visit Guruswami, again, what is it, about 2 years back, if I'm not mistaken, 2.5. And they started a project, and today's talk is a part of the outcome of that project. There is more to this work than just strong Converse, but Min will speak of the part that he chose. So, Min, let me hand it to you. Please go ahead. Welcome.
Okay, thank you. Thank you, Sasha, for the introduction. And also thank you for, I would like to thank the organizers for the invitation. So today, by the way, is my camera still on? Or?
No, the camera is not on.
Okay, great. So today I will talk about this a strong Converse theorem. I will prove it. A strong Converse theorem on bitwise decoding for random linear code ensemble. So as Sasha just said, this is so the Converse theorem that I will prove today. It is actually a small part of a joint work with Venkat Guruswami and his student Andrii Riazanov. So Andrii is Venkat's graduate student, PhD student. So this work was, I guess it started during my visit to CMU, and that was last year. So last year I visited to CMU for 1 month, visited Venkat Guruswami, and also happened to meet his student Andrii. So here are just some snapshots of my visit. This is that very famous statue called Walking to the Sky. It is placed in a very outstanding spot in the campus. I guess everyone who has been to CMU must have noticed this. And these two figures, these are just things that I have done with Andrii. So basically, it's like every day we spend 2 or 3 hours discussing our problems. I mean, Andrii and me, and then most likely we spend the whole afternoon or half of the afternoon just playing this stuff. There is an entertaining room. So I would say it's a very good experience for me. So when I prepared this talk 2 or 3 days ago, these things just come back to my mind. That's why I put a few figures and say a few words here to share this memory with you. Okay, so now going back to the technical stuff, my talk today is based on this paper. So if you are interested in reading this paper, here is the arXiv number. So this, as you can see from the title, is about polar codes. So the main thing we proved in this paper is that we rigorously proved that if we use polar codes with a large enough kernel, then we can achieve that so-called optimum gap to capacity, namely that 1/square root of n gap to capacity. I mean, this is order-wise optimum. Today I will talk a little bit about the main results of this paper towards the end of this talk, but not at the beginning. So at the beginning, I want to get right into the Converse theorem that I want to talk about. So as you can see, this is in fact a very long paper. I think it's over 60 pages. But the part I will only talk about a small part today. That is this section 6. Section 6, just 6 pages. So the Converse theorem that I will tell you today, it holds for general binary input channel with symmetric output. It holds for general symmetric channels. But today we will restrict ourselves to the special case of BSC, because number one, this is of course simpler and it is easy to do this presentation. But at the same time, this simple case of BSC already captures the main idea, the main non-trivial idea behind the proof for general channels. So let us just prove for this relatively simple case. All right, so let me introduce the notation now. We will use this vector v. We write vector v equal to v1 to vk. This is our message vector. And by the way, we are talking about code, so we just use the conventional vector, conventional notation, where the code dimension is k, is denoted by k. So this k is just the length of our message vector. Right? This is the code dimension, and these k message bits, they are basically the IID Bernoulli one-half random variables. These k message bits, they are mapped by a code book. They are mapped by a coding scheme to n channel inputs, So here in this talk, we choose the code to be random linear code. Basically, that means that we will pick a random matrix. G, we write it as capital G. This G is a binary matrix, namely every entry is binary. Binary entry matrix of size k times n. So k is our code dimension, and n is our code length. So after we have this message vector v, and this is encoding matrix G, after we have these two, then our channel input is just v times G. It's just v times G. This is the channel input. We write it as x. This is channel input. So x, it is a vector of length n. We write it as x1 to xn. And we put each of these channel input through a BSC channel W. And what we get is y1 to yn, a vector y, which is a channel output. Okay, so these are just the basic notation. By the way, these W's, as we just said, these W's, they are binary symmetric channel with parameter p. Namely, this channel, it flips a bit with probability p. Okay, so these are just the basic notations that we will use throughout this talk. Let's try to remember it again. So these v, x, and y, they are vectors. Okay, in particular, v is the message vector of length k. It's completely random. So each bit, the IID, each bit is a Bernoulli one-half. And then this G is this capital G is a matrix. It's an encoding matrix of size k times n. And again, we pick each entry of G independently to be a Bernoulli one-half random variable. And then our channel input is x equal to v times G. This is so x is also a vector of length n. Y is a vector of length n, and this is the channel output. So v, x, y are vectors, and G is a matrix. And when we write them in the capital form, we mean that these are random vector or random matrices. If we write the corresponding lowercase letter, like small v, small x, small y, then we mean that we are taking a realization of that random vector. If I write a small g, then I mean that I am taking a realization of this random matrix. So this small g is some fixed matrix of size k times n. Okay, so that's basically that's a setup for notation. That's a setup for notation. And I have recorded everything here. So K is code dimension, N is code length, G is random encoding matrix of size K by N, ID binary on half entries. V is a random message vector. X, channel input, X equal to V times G. W is BSC with parameter P, and Y is corresponding channel output. And we use this I of W, we use it to denote channel capacity. Okay, so now we are ready to state our theorem, So the theorem says this. It says that if your code rate is just a little bit above the channel capacity. So more precisely, if your code dimension is just larger than this n times channel capacity, it is larger than n times channel capacity by order square root of n, then square root of n times some logarithm, but let's try to ignore them, okay. Then with probability larger than 1 minus this very small quantity. How small it is? It is super polynomial in n, right? 1 minus this very small quantity over the choice of G, it holds that the conditional entropy of every VI of every message bit given the channel output is very, very close to 1. Again, how close? It is the difference to 1 is again this very, very small thing that is super polynomial in n. Okay. And this holds for every message bit. So one thing to notice here is that this conditional entropy, it depends on the realization of G, right? Because this conditional entropy, it depends on your codebook. It depends on your codebook, and your codebook is completely determined by this generating matrix G. That's why we say that with this probability over the choice of G, it holds that this conditional entropy is lower bounded by 1 minus this very small quantity. So in this talk, we will prove this theorem, and in particular, we only need to prove that conditional entropy of V1 given Y is larger than or equal to n minus n to the minus log n power. We only need to prove this. We only need to prove that this holds with this amount of probability, and then the theorem statement just follows directly from a union bound, right? Follows directly from a union bound. So in the rest of the talk, I will show you how to prove this. Conditional entropy.
This is Prakash. How are you? This is a question.
Uh-huh.
This result automatically implies a lower bound on the bit error probability for each I, right?
Yes.
Decoding bit error probability, right?
Yeah, I guess by Fanon's bound.
I'm wondering, yeah, it should be true, right?
Yeah.
Okay, all right, thanks.
Okay, yeah, I think that's true, but yeah.
I also have a quick question. I mean, it seems as though this should be known. How come are you sure nobody addressed it previously?
At least we didn't find it. I mean,
a very basic claim. I would say, going back to the 1960s, should be someplace there, no?
I'm not sure, because you see, there was a paper by Neri Merhav, I think 10, 15 years ago, where he did a weak converse on the average bit error probability. And he would have cited anything prior to that had the result been known. So as far as I know, even the bit error average bit error probability is a weak converse. I think it was Neri, in one of Neri's ISIT papers that I found it. And Lynn might remember this was a homework problem in the information theory classes here in Maryland. They just used two things, the funnels and the data processing lemma and a couple of clever manipulations. So I'm not sure this was known before that.
Not that I know any sources. It just sounds so basic that I couldn't, keep from asking. Okay, fine. Thank you.
Okay. So yeah, if anyone from the audience have seen this before, yeah, it's better that you can tell me so that we can state it. We can cite it properly in the paper. But to the best of our knowledge, we haven't seen it before. Okay. So the first.
Sorry to interrupt. I just wanted to clarify that the result that that Neri had, the one that I saw, maybe there were results before that, arbitrary codes for arbitrary discrete memoryless channels. So it didn't have to be a linear code. And in fact, it was for fixed codes. So no randomization over the choice of codes. So you have the bits that you had VK, V1 through VK, and then they were mapped by a fixed encoder into a code word sequence of length n. And then he did the analysis. So the randomization was not needed in his argument.
So it somewhat diverges from this claim because on the one hand, it is for any code, but on the other hand, it's the average bit error probability.
That's right, yeah.
And this is different. This is for every bit, but for a random code.
Sure, yeah, right.
Okay. Okay, so the first question you might want to ask about this Converse theorem is that why do we restrict to random linear code ensemble? Because you see, when you state the Converse theorem, usually you want it to hold for any code, right? You want it to hold for any code. But here, the reason we restrict to random linear code ensemble is that this theorem, this statement, it is simply not true if you don't put any restriction on the code structure. So I can give you a very simple example. So now let's say you have this message bit V1 to V1, V2, V3 to VK, and you have your channel input X1, X2, X3 to all the way to Xn. So I can show, and then you of course transmit through the channel with some capacity, with some certain capacity. Doesn't matter. I can show you that a very simple construction that no matter how high your code rate is, you can always transmit this bit. You can always choose a bit, any bit, choose a bit, and transmit it through the channels in perfectly. So how do you do it? Well, it's very simple. All you need to do is that you choose the first log n bits. You choose the first log n bits, and you just repeat this V1 into every one of them, right? You make X1 equal to V1, you make X2 equal to V1, you make X3 equal to V1, all the way down to X log n equal to V1. And then for all the other bits, you just map them to the rest of the channel input in arbitrary way you want. For the rest of the message bit, you map it into the other channel inputs in arbitrary way you want. So in this way, you can see that clearly because that when the code length goes to infinity, this log n also goes to infinity. In this way, as long as your channel is not completely noisy, you can always transmit this bit V1 perfectly, right? So you can see just through this simple example, you can see that if you don't put any structure, any restriction on the code structure, then that statement is simply not true. So yeah, so if you want to prove such a theorem, such a statement, you have to restrict to certain code structure or certain code ensemble. And for the purpose of our paper, we choose to prove it for random linear code ensemble.
But this construction can be also done for a linear code. It's the random ensemble that does the job, right? That is the separator.
Yeah,
you can repeat a bit easily in a linear code. This is no challenge, right?
Yeah, it can be linear or non-linear, doesn't matter, yeah.
So what matters is the randomization.
Yes, the random. I would say, I would guess you can certainly come up with other structures or ensembles that satisfy this. I would guess that you would require certain kind of symmetry among these message bits.
Yes.
But just for the purpose of our paper, we just use random linear code ensemble. Yeah. Okay, so this is the first remark, first explanation about our theorem. All right, so let me also tell you how the high-level plan. So the high-level plan is just to prove that this expectation is very close to 1, namely larger than 1 minus some m to the minus log n power. I want to prove this. And then with this bound, together with the fact that this is something that is upper bounded by 1, you use this bound together with that fact, and then you use Markov inequality, then easily you can get what we want to prove. Okay, so for the rest of the talk, I will prove, basically I will prove this inequality. So the first step is, of course, you just write things out explicitly. So in these two equations, just follows from the definition of this formula. So you see here, I just copied this sum over G here. Nothing has changed. So if you look at this big bracket, this is precisely the definition of this conditional entropy, right? This is precisely the definition of this conditional entropy. So one thing I should emphasize here is that you look at this probability of y equal to y, I write a superscript G here. Why do I do so? Because this probability depends on the realization of your codebook, right? This probability depends on the realization of the codebook. Namely, it depends on the realization of the generating matrix G. That's why I put a superscript G here. So the other things are just very standard. I will not say much more about it. And then in this equality, I did nothing. The only thing I did is I removed this bracket. And then I take this summation outside. Okay, so that's the only thing I did. So here is what we get. This is a precise expression of this expectation. Okay. So next. So up till now, this is what we get on last page. So here I want to tell you a somewhat surprising thing. That is, you can, in fact, you don't change anything else in the formula. You don't need to change anything else in the formula. This guy remains unchanged. This guy remains unchanged. These two summations remain unchanged. The only thing you need to change, you can change, is this unconditional probability. It turns out that you can, here in this equation, you can replace this unconditional probability with this conditional probability. And you still have this equality. You can just replace this unconditional probability with this guy for free. In other words, you can simply, what does this mean? It simply means that you can just assume that your channel output is produced by the 0 input. So here my message V equal to the 0 vector implies that my channel input is also the all 0 vector. Okay. So this equation tells you
term by term identity, or is it because of the sum? It's term by term, right? Is that what you're saying?
This requires a proof. I will show you the proof towards the end of this talk. So by now, let's just assume that this is true and let's finish the proof. And then after we finish the main body of the proof, I will show you how to prove this equality a bit later in the talk. It requires a proof.
Is it true that this probability for an individual little y is the same as the conditional one, or do you need the sum?
That's what I was asking. Is it, if you fix little y and little t?
No. You definitely need the sum. You definitely need the sum.
Yeah. All right. Good. That's good. Yeah. Thanks.
Okay. So the nice thing of replacing this guy with this guy is what? Originally, if you just write it in this way, originally you have this probability depends on your codebook, depends on the generating matrix G, right? This probability depends on G. But here, this probability, it has nothing to do with G, because this probability only depends on the Hamming weight of Y, right? Because your channel input is all zero vector and your channel output is Y, and you're transmitting through a BSC channel. So of course, the transition probability is just a function of the Hamming weight of Y. And this will significantly simplify all the analysis. Okay, so this is what I just said. This conditional probability doesn't depend on G. It only depends on the Hamming weight of Y. And here, I just write it out. Here, I just write it out. Okay. So this, if you write it out, it is just this thing. P raised to the weight of Y's power and times 1 minus P raised to the n minus weight of Y's power. Okay, these two are equal. These two underlying terms are equal. And then you see that this term has nothing to do with G, right? This term has nothing to do with G, which means that you can put this summation of G here. You can move the summation of G here. And once you move summation of G here, you immediately realize that the summation of G, summation over G of this product is precisely the expectation over G of conditional entropy of V1 given Y equal to small y, right? So as I said at the beginning of this talk, this conditional entropy, it depends on the codebook. It depends on the realization of your generating matrix, this small g, right? So now we have this further simplified form. So you look at this equation.
Min,
one way.
Hi, Min. May I ask a question, please? Going up to your slide, when you go from the first equality to the second one, where you introduce a condition on V equal to conditioning on V equal to 0, does that use also the specific nature of the channel, the symmetry that you assumed, or is this true in general?
It is this equality is true for any BMS channel. So you need to have a symmetric property of the channel. It doesn't have to be BSC, but it has to be a symmetric channel.
Okay, good, thanks.
Yeah, I feel that Prakash is already knows how to prove it. Okay. Okay, so now you look at this equality. You look at this expression. It is helpful in the sense that now you only need to focus on the so-called typical Y. So what is a typical Y? Simply a typical Y simply means that your weight of Y is very close to n times P, very close to n times P. So if you can prove that for this kind of typical Y, this quantity is very close to 1, you only need to prove it for this typical Y. As soon as you do that, you can see that this whole sum is also very close to 1. It's also very close to 1. So yeah. So this is what we will do next. So more precisely, we say that output Y is typical if its Hamming weight, the difference between its Hamming weight and NP is upper bounded by 2 square root of n times log n. Okay. This is very typical. And what we will prove is that for this typical Y, for a typical Y and a typical G, we will define what is typical G later. We will define what is typical G later. But typical Y is a Y that satisfies this inequality. For typical Y and typical G, we will prove that this conditional entropy is more or less equal to 1. So this conditional entropy is just this conditional entropy is equal to the binary entropy function of the probability of V1 equal to 0 given y equal to y. So this is a binary entropy function where h of p is equal to what? Minus p log p minus 1 minus p times log 1 minus p. So this is a binary entropy function. So by definition, this is just a binary entropy function of this conditional probability. And here I am just writing out this definition of this conditional probability. So to prove that the binary entropy function of this this quantity is more or less 1, it is equivalent to proving that this ratio is more or less equal to 1/2. Is more or less equal to 1/2. So next we will try to write out this ratio explicitly. So basically, let me give you an overview. So basically, this is I have a message vector v. I have a message vector v, v1, v2 to vk. So if this message vector take all the possible 2 to the k possible values, it corresponds to 2 to the k code words, right? It corresponds to 2 to the k code words, and that is our codebook C. That is our codebook C. And then if I fix this v1 to be 0 and only vary the other k-1 bits, then I get half of C. Right? Let's say it's this half. And maybe we can call it C theta. We can call it C theta. Okay. So basically, this is this probability of G, y equal to y. You can write it as summation of every x in the code book. So x is the channel input, so every x in the code book. Probability of y equal to y, x equal to small x, And here, this is the denominator. For the numerator, you can write Pg v1 equal to 0, y equal to y. This is the summation of x in C theta, where we restrict the first bit, where here we restrict the first bit to be 0, and this C theta is the resulting codebook, half of the codebook. Okay. P y equal to y, x equal to x. And you can see this joint probability, it can always be written as this conditional probability multiplies with 1 over 2 to the k. Same here. Conditional probability multiplies with 1 over 2 to the k. So now from this equation, it should be clear that, and by the way, this constant 1 over 2 to the k, they just cancel each other, right? Because one is on the numerator, the other is on the denominator, so they just cancel each other. So this is what's left. This is what's left. And you see this conditional probability, it only depends on the Hamming distance between x and y. So therefore, if we want to calculate this ratio, the only thing we need to know about the code is the distance distribution from the code, from all the code words. This is all my code words, from all the code words to my y, right? I need to know, if I want to calculate these probabilities, these ratios, then I only need to know the distance distribution between y and all my code words. Okay, so that's what I do. That's what we will do on the next page.
It's
So
the coset weight distribution, right?
yeah, you can think of it as a shifted distribution, yeah, shifted weight distribution.
Coset,
Yeah,
so
yeah.
there were papers on this in the 80s for typical coset weight distribution for linear codes. It's basically, yeah, this is more or less, you know, non-calculation.
I see. Yeah, I wouldn't suspect that. That I would believe. Yeah.
Mm-hmm.
So so this BG dy, it is just you fix the code book, fix the generating matrix G, you fix the output Y, and this is the total number of code words that has Hamming distance D from Y, right? You have your whole code book here. This is your whole code book, and this is Y. And then this BGDY just count how many code words are there in this code book such that the distance from Y is D. Its Hamming distance from Y is D. So how many non-zero code words are there? We are excluding the zero code word here. So now this B theta dy, it has a very similar meaning. Remember that we have half of our code book. We call it C theta. This half is obtained by restricting this V1 to be 0, right? By restricting V1 equal to 0, we get this half of the code book. And this B theta is just counting the number of code words in this half of the code book, in half of this code book. Okay. So basically this V theta, what is this V theta here? You have V1, you have your vector V, V1, V2, V3, Vk. So basically we call this k minus 1, we view it as a new vector V theta. This k minus 1 components, we just view it as a new vector V theta, right? That's V theta. And this G theta is just, you know, originally you have a matrix G, you have a matrix G, K by N. So now this G theta, it is just removing the first row. You just remove the first row, you get G theta. Okay. So this is just explaining the notation, but I guess you can already understand it from these figures. Okay, then with this notation, we can formally write out this ratio. So we have already derived this step. So the next equality is obtained as follows. So this first term corresponds to the zero code word, corresponds to the all zero code word. So the transition probability is just given by this, determined by weight of Y and given by this expression. And then for the rest, we just make use of this shifted weight distribution to express the sum of all these transition probabilities. Okay. So this should be clear from the definition. Okay. So next, let us try to look at this formula more carefully. I just copied this formula from the last page. Let's look at this formula more carefully. So a simple observation here is that if there are two terms here, if this term is the dominant term, if this term is much larger than these two terms, okay, if this is much larger than these two terms, then what does it mean? It means that this ratio will be more or less equal to 1, right? It means that this ratio will be more or less equal to 1. And in this case, it means that if you take the conditional entropy of V1 given Y, and under the condition that this ratio is more or less equal to 1, then this implies that this conditional entropy is more or less 0, meaning that you you will know what's the value of V1 from the value of Y almost surely. Okay, and this is not a surprise. This is not a surprise because remember that from our from this equation, actually we are assuming that, right, or from here, actually we are assuming that this Y is produced by the all zero input. So here, if this term is a dominant term, it means that the true input, if this term is a dominant term, it simply means that the true input dominates all the other fake inputs, right? Dominate all these other inputs, they are false inputs. They are not true inputs, they are fake inputs, right? If your true input is a dominant term, then no doubt that this, it's not a surprise that this conditional entropy will go to 0. You will be able to distinguish V1 very clearly. So this is the first case. So the second case is that the second term becomes the dominant term. These two terms become dominant, right? So this first term is much less than both of them. In this case, you can just later we will show that this ratio will just become more or less 1/2. So the conditional entropy of V1 given Y will become 1, right? And again, this is because the contribution from all these fake inputs, they dominate the contribution. They are much larger than the contribution from the true input. So so you get that the ratio become 1/2 and the conditional entropy become 1. And let's very quickly see why when we only have these two terms, the ratio becomes 1/2. Let's quickly see why this happens. Well, this is not this is a very commonly used trick when you analyze random linear code. You just write this. This is a counting function, right? You are counting how many code words is of distance d from your output y. So it can just be written as the sum, right? How many non-zero code words? So we are taking the sum of v not equal to 0. We can just write it as the sum of all these indicator functions, So basically it's sum over all the non-zero code words. And you can see that of course, because each non-zero code word is completely random. So the expectation of every indicator function here has the same value. The expectation has the same value. So that value is the probability that you pick a completely random, this Vg plus y, it is, so basically when G is random, this Vg plus y, it will be a IID 1/2, Bernoulli IID Bernoulli 1/2 length n vector, right? So what's the probability of IID length n, x1, let's say you have x1 to xn, they are IID Bernoulli 1/2. So what's the probability that the Hamming weight of this vector is d? Where that is simply n choose d divided by 2 to the n. That is simply n choose d divided by 2 to the n. So this is the expectation of a single indicator function. So by linearity of expectation, we know that the expectation of Bg is 2 to the k minus 1 times this thing. 2 to the k minus 1 times this thing, right? So now let us try to calculate the expectation of this whole sum. Let's try to calculate the expectation of this whole sum. So all we need to do here is just to plug in this formula, right? Plug in this formula. So we take this 2k 2 to the k minus 1 and 2 to the minus n. We take them out, and we do this summation over d. And this is this sum by the binomial theorem. This is 1, clearly. So what's left is just 2 to the k minus 1 times 2 to the minus nth power. And very similarly, you can show that if I put a theta here, the expectation of bg dy, if I put a theta here, pd1 minus p, this expectation just becomes 2 to the k minus 1's power minus 1 times 2 to the minus n, right? Mm-hmm. Because in the calculation, basically nothing changes except for the cardinality of the cardinality of this set. The cardinality of we get a 2 to the k minus 1 here because the cardinality of the whole code book is 2 to the k. And we get a 2 to the k minus 1 here because the cardinality of half of the code book is 2 to the k minus 1, right? And then with this calculation, if you just place, let's just assume for now that this quantity is very tightly concentrated around this expectation. Assume that this is true, then you can easily see that y, the ratio between these two is more or less very close to 1/2, right? Because this is essentially 2 to the k minus 1 divided by 2 to the k. So that is just 1/2. Okay. And from this calculation, it should also be clear that when this will be the dominant term and when this will be the dominant term. So basically, we know that the magnitude of this term, assuming that it's very tightly concentrated around the expectation, then the magnitude of this term is just more or less 2 to the k minus nth power. That's more or less equal to this. Multiplies with some constant, doesn't matter. Multiplies with some constant. And now suppose that we have a typical y with a typical weight. Then the typical weight is just more or less equal to np. In this case, this thing just becomes, this quantity will become 2 to the minus n times hp, right? When we have a typical y, this term is more or less 2 to the minus n times hp's power. So now we compare these two quantities, right? So it is clear that when this minus n hp is larger than k minus n, when this happens, then this is a dominant term. Then the true code word, the contribution from the true input becomes the dominant term. And this happens when k is less than n times 1 minus hp, and this is precisely n times the channel capacity, right? So you can see just from this heuristic analysis, you can see that when my code rate is below, although it doesn't quantify how much below you need, but you see when it is below this channel, when the code rate is below the channel capacity, this guy becomes the dominant term. When this guy becomes the dominant term, this ratio becomes very close to 1 and the conditional entropy becomes 0. You can perfectly decode this V1. You can perfectly decode this bit. On the other hand, if we change the direction of this inequality, if k is larger than, if the code rate is a bit larger than the channel capacity, then these two guys will become the dominant term, and we can simply ignore these two. When this happens, as I have just calculated, the ratio between these two will be very close to 1/2, and when this happens, the conditional entropy is very close to 1, very close to 1, meaning that you cannot, basically you know nothing about this bit V1. You know nothing about this bit V1. Okay. So this is just a heuristic, somewhat not rigorous, non-rigorous analysis. Next, I will try to make this argument more rigorous. So the main idea is that since we are in the regime of slightly above the capacity, so as I just said, we will be able to show that this term can be basically it can be ignored. It can be ignored. It's very, very small. We will show this. And then for these two sums, what we will do is that we will prove that these two sums are very tightly concentrated around their expectation. Very tightly concentrated around their expectation. So to prove that this shifted weight distribution tightly concentrated around their expectation, this technique is not new at all. People have used it for decades, and but for the sake of completeness, let's just go over it again. So we have already written this BG as the sum of indicator functions. So one thing to notice is that these summands, they are pairwise independent. They are pairwise independent. So these summands are pairwise independent. Why is that? Because if you take two distinct code words from your code book, since we have a linear code, then their difference is also a code word from a non-zero code word from this code book. But every non-zero code word in a random linear code is a completely random vector, meaning that it is an IID Bernoulli 1/2 vector of length n, right? That's why each summand here, each indicator function here, they are independent because the difference of any two vectors here, they differ by a completely random vector. Okay, so under this condition, under this observation, we know that the variance of the sum so this is variance of sum of pairwise independent random variables. Since they are pairwise independent, so the variance of sum is equal to sum of variance, right? It is equal to sum of variance. The variance of sum is always equal to sum of variance. But here, this is a Bernoulli random variable. For Bernoulli random variable, we always have that the variance is upper bounded by the expectation. And we know what is the expectation. The expectation is just n choose d times 2 to the minus nth power, times 2 to the minus nth power. So here, the variance of BGDY, it is equal to sum of variance, and this is further upper bounded by sum of expectations, right? Because of this inequality. This is further upper bounded by sum of expectations. And then this sum of expectations by linearity of expectation, you can see that this is precisely equal to the expectation of BGDY, BG dy, right? Just this follows from linearity of expectation. So here we know that each expectation of each individual indicator function is n choose d times 2 to the minus nth power. So the expectation of this sum is just 2 to the k minus 1 times the expectation of the of each individual term, because we are summing over 2 to the k minus 1 non-zero message vectors. So here, then, once we get this, we want to prove that this BGY, this BG dy is very close, is equal to 1 plus small 1 plus a very small term times its expectation. We want to show that this holds with high probability. And when this expectation is much larger than 1, we can prove this. Just simply using Markov inequality. Using Markov inequality. Why? Because the deviation, the standard deviation of BG dy from its expectation is the square root of this thing, right? And it's further upper bounded by square root of this. So if this thing is much larger than 1, then it basically means that this deviation compared to the expectation itself is very small. So you can write it in this way. But this only happens when this term is much larger than 1. This only happens when this term is much larger than 1. For example, if you have this expectation is equal to 3, then you can never claim this. You can never claim this equality, because when this is equal to 3, then this only tells you that this variance is upper bounded by square root of 3, but it can still take value of 2 or 1 with certain probability. So when this expectation doesn't satisfy this inequality, we do not really have tight concentration. We do not really have tight concentration. So what should we do? So what should we do now? And clearly there are value of these which doesn't satisfy this this inequality. For example, if you take d equal to 1, then certainly this inequality doesn't hold. But luckily, we don't need to prove tight concentration of BG dy for all d. We don't need that for all d. We only need that for a small range of d. And for those d's where this expectation is small, we don't even need the tight concentration, because when this expectation is very small, a simple Markov inequality will suffice. We don't even need the tight concentration, right? And that is explored in this decomposition. So basically, we decompose this sum over d into 2 parts. The first part is the so-called negligible part. The first part is the so-called negligible part, and the second part is the substantial part. So why do we call the first part the negligible part? Because if you take expectation here, if you take expectation of this first part, you can easily show that this expectation is very small compared to the expectation of this whole thing. The expectation of this part is negligible compared to the expectation of this whole thing. So for this part, we only need to use a Markov inequality to bound its magnitude. So this is really the part that contribute the most to this sum. And for this part, only for this part, we need tight concentration. We need tight concentration. Okay, so let us start with this negligible part. So basically, the analysis of this negligible part is just an application of a Chernoff bound for a binomial random variable. Okay, so
I mean, I'm sorry, this is probably somewhat anticipatory question. Sorry about that, but I thought that this BG does not depend on P, and then it may be that it is still a small number when D is in the neighborhood of NP, and then your non-negligible part it's still, so there is still no concentration.
we will be able to show that as long as this holds, you will have concentration.
So concentration occurs basically when this number grows, I don't know, exponentially or somehow. And if you look at the formula, this is really the same as the weight distribution of the code itself. And
yeah. That's right. That's right. Yeah.
Yes. And well, there is little something that is missing, but I'm sure you'll say this. Sorry for the interruption.
Okay. Okay, so this negligible part, let us just write it as ZG of Y. Okay, this is the sum. And let's try to calculate the expectation of this sum. Where we have done this before because we have seen this before. The expectation of this thing is 2 to the k minus 2 to the k. The expectation of this thing is 2 to the k minus 1 times n choose d times 2 to the minus n, right? So this is the expectation of an individual indicator function, and this is the number of indicator function in the sum. Okay, so this is the expectation of this term. So I just take it into this formula, and this is what we get. This is what we get. I take this 2 to the minus n here. So this is what this goes here. This part, it goes here. So n choose d goes here, right? And then what's next? The next thing is to observe that this is just the probability of a binomial random variable has a somewhat large deviation from its mean value, right? This is just a probability of the minus NP larger than 6 times square root of n times log n, where z is a binomial distribution with parameter n and p. So this probability by Chernoff bound, this is it can be upper bounded by what? Maybe by 2 times exponential of square of this thing divided by 3n, right? So this, so you see this square root of n, it just disappears. So what's left? So what's left is exp 12 log n square. So this is what's left. And this is further equal to 2 times, you take 1 log n down, right? Exponential of log n is equal to n itself. You take 1 log n down. So this is 2 times n raised to the minus 12 log n's power. So okay, I'm missing a minus sign. Minus. Okay, so yeah, so this is what I get, right? This is 2 times n raised to the minus 12 log n's power. And this is a constant that I just copied here. So remember that this part is the expectation of the whole sum, namely the sum of all value of D. This is the expectation of the whole sum. So you can see that the expectation of this negligible part is really negligible compared to the whole sum, right? So for here, by this inequality, what we need to do next is just a Markov inequality, right? Very standard thing. You just define the set G1 to be the set such that this negligible part is upper bound by this quantity, and then by Markov inequality, you know that the probability that G belongs to this G1 is very, very large, very close to 1, very close to 1. Okay. So that's the analysis for the negligible part. So for substantial part, we just, as we have seen, as I have said before, we need to use again use Markov inequality. In fact, Chebyshev inequality. So here, the probability that the deviation of BGDY from its mean value is larger than this quantity by Chebyshev inequality, this probability is upper bounded by this value. Right? On the numerator, you have the variance. On the denominator, you have the square of this thing. And in this equality just follows from the fact that the variance of BG is less than or equal to the expectation of BG. We have just shown this. This equality just follows from the fact that the variance is upper bounded by expectation. And finally, here we plug in the value of the expectation. Expectation of BG. This is equal to 2 to the k minus 1 times n choose D times 2 to the minus n. So, okay, for simplicity, let us just ignore this minus 1. So here it just becomes k minus n. Here it just becomes k minus n. So you plug it in here. So on the denominator, you get n choose D. On the numerator, you get 2 raised to the n minus 1, where plus 1. You can add plus 1 here. The inequality still holds. So now let us try to show that this quantity is very, very small. When remember that in the theorem we assume that k is larger than or equal to n times the channel capacity, which is 1 minus HP, plus 8 times square root of n times log square n. That's our condition in the theorem. So here we have n choose D on the denominator. So n choose D, we know that this is more or less equal to 2 to the n times h of D over n. So this h is a binary entropy function. So this is equal to 2 to the n times HP plus n times h D over n minus HP. But here, look, here we have this condition. The difference between D over n and P is upper bounded by 6 times log n divided by square root of n. The difference is upper bounded by this value. So it turns out that I will not prove this for you, but you can believe me. as long as you have this condition, this term can always be upper bounded by some constant. Let's say it's constant C0 times log n square divided by square root of n. You can always prove this. And then you multiply it with this n. You multiply it with this n, so this square root of n moved up. It moved up. So what do we have now? What do we have now? Let's try to compare this whole thing. So this is m to the 4 log n multiplies 2 m minus k plus 1. Further multiplies 2 to the minus nhp minus something minus plus, let's say plus theta of square root of n log square n. So this is what we get. This is what we get. And let's ignore this one here. Let's ignore this one here. From this inequality, we have n minus k is upper bounded. N minus k is upper bounded by n times hp minus 8 square root of n log square n. We have this. So this n minus k is upper bounded by nhp times minus 8 times square root of n log square n. So you can see that the n times hp here cancels with this minus nhp. So these two cancel with each other. So what's left? So what's left here is minus 8 square root of n times log square n. That's on the exponent. But here we have something of the same order, but through a careful calculation, you can show that the constant in this term is less than 8. So what's left? In fact, you can show that the constant in this term is less than 6. So what's left is a minus 2. What's left here is 2 to the minus 2 square root of n times log square n. And clearly, this is much larger. The exponent here is much larger than the exponent in this term, because the exponent in this term is just log square n. So just now we have shown that this is less than or equal to n raised to the minus square root of n log n. Just now we have shown this. This is less than n raised to the minus 2 times square root of n times log n. And then again, by application of the Markov inequality, no, not application of Markov inequality. This is, yeah, basically this is what we have just shown. So we have just shown that this quantity is upper bounded by this value, And then this holds for a individual d in this range. And then by you can apply a union bound and define a set G2 such that this holds for all values of d in this range. And then you apply a union bound, you can see that the probability of G belongs to this set G2 is 1 minus n raised to the minus square root of n's power. 1 minus n raised to the minus square root of n's power. So now we have, basically we have all the ingredients that we need. So next, let us try to put everything together. Let us try to put everything together. So you can see that as long as G belongs to the intersection of G1 and G2, this sum is dominated by the substantial part. And since we assume that G belongs to G2, the substantial part again concentrates very tightly, around its expectation, right? And the difference, you see, so basically this G2 means that the difference between BG and its expectation is this n to the minus 2 log n times the expectation. So you can equivalently write that BG dy is 1 plus minus n to the minus 2 log n times the expectation of BG. So this would immediately imply that here this sum is also very tightly concentrated around its expectation. This is 1 plus minus n to the minus 2 log n. This is a condition from the definition of G2, right? Times the expectation of this sum. And we have just shown that, we have shown it maybe more than once, that this expectation is equal to this value, So yeah, so here is just one way to write out this bound, just one way to write out this bound. We have also shown that the probability that G belongs to this good set, namely the intersection of G1 and G2, is lower bounded by 1 minus this small quantity. And very, very similarly, we can also show that with this probability over the choice of G, this BG theta is also very tightly concentrated around the expectation. And the expectation of BG theta, of this sum for BG theta, is this value. So now let us going back to this formula that we have seen at the beginning of this talk. We have proved that these two guys has we have get a very tight bound for these two guys. So this guy is more or less 2 to the k minus 1 times 2 to the minus n, and this guy is more or less 2 to the k minus 1 times 2 to the minus n's power. So the next thing, the only thing we are left to show is that this part is much less than this product. Or that's, for the sake of simplicity, we can just ignore this minus 1 here. So all we need to show here is that this guy is much less than 2 to the k minus n. Than 2 to the k minus n. And recall that we only need to prove this for the typical y, and the typical y meaning that the Hamming weight of y deviates from NP by at most 2 times square root of n times log n. So this thing, again, this is a very elementary inequalities that I want to dig into the details into this stuff. So just trust me that as long as you have this condition, weight of y deviates from NP by at most this quantity, you will always be able to show that this thing is upper bounded by 2 to the minus n HP. So this 2 to the minus n HP, this is the value for when the weight of y is precisely np, right? But now you allow this kind of deviation, so you will have this extra term here. You will have this extra term here. And then after some simple calculation, you can show that this is further upper bounded by this quantity. So how do you get from here to here? So let's do it. Because here you can simply view it as 2 to the k minus n, and our k, remember that this is larger than or equal to n times 1 minus small hp plus 8 times square root of n log square n. So this means that k minus n is larger than or equal to minus n hp plus 8 square root of n log square n, right? So you compare the component is here. So you compare this quantity with this quantity. So you can see that clearly this guy is larger. This guy is indeed larger than this, right? So we have shown that under this condition, where k is slightly above the capacity, under this condition, this first term is indeed much less than the second terms. So this ratio is basically dominated by the ratio of the second term, which is very close to 1/2. And how close is it? It is the difference. The difference is upper bounded by this quantity, right? The difference is upper bounded by this quantity. So okay, so here we really have everything we need. We have shown that for a typical y, this quantity is larger than or equal to 1 minus n to the minus 2 log n. We have proved this for all y such that weight of y minus np is less than or equal to 2 square root of n log n. So now the next step is to observe that this whole thing is larger than or equal to the sum of y such that it satisfies this inequality. And for all such y, we have proved this lower bound. So we can simply put this lower bound here times 1 minus n to the minus 2 log n. But now you notice that again here, by the Chernoff bound for a binomial distribution, this probability is larger. This probability is larger than or equal to 1 minus n raised to the minus log n. Again, you apply that Chernoff bound for binomial distribution, because here, yeah, this is just Chernoff bound. This thing multiplies with this thing. So eventually, we have shown that this expectation is indeed larger than or equal to 1 minus n times log n. So I'm omitting some constants. And then by a simple application of the Markov inequality, you can show that we have completed the proof of our theorem. We have completed the proof of our theorem. So maybe I can stop here to see if you have any questions up till now. So if not, I can very quickly go through the proof of that lemma, where we recall that we use this lemma so that we can restrict to the zero input. We can restrict to the zero input. More precisely, we can replace this quantity, this probability, with this conditional probability. So the first step to prove this lemma is, of course, writing out the explicit expression, So here, in this formula, I really did nothing. All I did is to write this PG of y equal to y. I write it as this sum. Right. So I write this marginal distribution as the sum of all this conditional distribution multiplies with the marginal probability of v equal to v, which is 1/2 to the k. Right. So this is what I get. So all the other things I didn't change. PG of g is just falls in here. And this thing is just this conditional entropy. This thing is just a conditional entropy. So now we have this expression, and next I will show you that for any fixed codebook G and fixed vector V, we always have this equality. You see, we have the summation over y. Here, originally, we have the conditioning on v equal to some small v. But it turns out that for any v here, we can replace it with the all zero vector. So as long as we have this equality, our conclusion will hold by simply replace this v equal to v by v equal to 0 in this expression. So if I just replace v equal to 0 in this expression, then this sum just disappears. This sum becomes this whole thing just disappear, right? You have 1/2 to the k, and you do this sum 2 to the k times, but actually the summand has nothing to do with this small v if you replace v equal to 0 here. So this sum, it just disappear. And in fact, what's left is precisely what we want, right? You replace that unconditional probability of y equal to y with this conditional probability of y equal to small y, conditioning on v equal to 0. So all we need to prove next is this equality. And this is the equality from the bottom of the last page. And this, in fact, follows directly from this equality. So let's see why is that. Now, let's assume that this equality holds. And under this assumption, then you can clearly see that it implies this equality. Why is that? Because from this equality, you can write y equal to small y plus vg here, plus vg everywhere, right? So now this follows directly from this equality. But now you are summing over all possible y's. So this is equivalent to summing over all possible y plus vg. So you can simply remove this plus VG in the summation. So as soon as we can prove this, we are done. As soon as we can prove this, we are done. So next, let's see how to prove this. How to prove this equation. So first of all, these two quantities, they are clearly the same. These two quantities, they are clearly the same because V equal to V is equivalent to the channel input is equal to VG, right? The channel input is equal to VG. So the distance between VG and Y, distance between VG and Y is precisely the distance between Y plus VG and 0. So these two probabilities, conditional probabilities, they are exactly the same, no doubt about it. So what about the other part? What about the other part? So these two binary entropy functions, they are also equal to each other. That is simply because we are facing a linear code, and the linear code is translation invariant. So now you are translating this. You have output Y. You have output Y, and you have a code word. You have a code book C, and you have half of the code word C theta. You have half of the code word C theta. So this, as we have already written out, this is a probability of Y equal to small y. This is equal to summation of probability small x, where x belongs to the code book C. So this is the summation of all these conditional probability where x take all possible vector in the code book. X take all possible vector in the code book. But now, essentially, if you look at here, if you replace this y with y plus vg, that is, you replace y with y plus vg. That is in fact equivalent to keeping y to be the same, but replace your x with x plus vg, right? But replacing x with x plus vg. So let's write it out explicitly. X equal to x. This is the same as the conditional probability of y equal to small y, but I shift this x with vg. But now, since vg itself is a code word, right? vg itself is a code word, and I am summing over all the code words. So here in this summation, I can just view this x plus vg. I view it as a new variable, and this new variable, it still ranges over all the vectors in the code book. So these two quantities, they are really the same. They are really the same. And similar, very similar analysis goes through for the numerator. There is only one small, very small subtlety. That is, when this VG, remember we have a code book C, and we have this subspace of this code book we call the C theta. This is all the code words obtained from restricting V1 equal to 0, right? When this VG belongs to this C theta, then this part is precisely equal to this part. But when this VG belongs to the other half, namely when this VG belongs to C minus C theta, then this guy is in fact equal to the probability of V1 equal to 1 and Y equal to small y. You can just play with it a little bit, and you will realize this again by the translation invariant property. Because in this case, VG is just representative from a co-space, a shifted space. Okay, so I guess that's all for the proof of why we can restrict to the 0 input, right? Because as soon as this is proved, we will have this equality. And with this, I think the proof of the bitwise converse is complete. So as I said at the beginning of this talk, this converse theorem holds for any BMS channel, not just BSC, as long as your channel can be written as a combination of several BSC channels. This theorem will hold. So I also prepared a few more slides about the results in our main paper, but in fact, I think I'm running out of time, so maybe it's better for me to just stop here and take possible questions. Thank you.
Thank you. Therefore, the conditioning on the 0 input, that's true for every G. So it's the summation over Y which averages things out, right? You had a double sum over G and V. I'm sorry, G and Y, Yn, and it's the summation over Yn that is critical because this is holding for every G, every little G. Yes.
You're talking about here or?
Here, but the original statement that you wrote at the very beginning, somewhere here, right? No, even before that, I think there was a double.
I think. Are you saying that do we really need this sum over Y? Is that what?
No, this is good. So this is true for every G, right? But didn't you have a double sum somewhere? I think earlier on.
Yes, I have.
Yeah. So what I'm saying here is that it holds for every G. Actually, it's the summation over Y that is crucial.
Oh yeah. Summation over Y that is crucial. That's right. That's right.
Right.
Yes.
Thank you. It's a very clear talk. Thank you very much.
I agree, right. I mean, for these symmetric channels, linearity still plays a role, right? As long as the uniform distribution is good, we still can play somewhat similar game, right?
By that, you mean restricting to zero? What precisely are you referring to?
Well, more or less this argument, the weight distribution is still relevant. That's what I'm saying. Is that correct?
I think it's slightly more complicated.
No, it's not.
We still have all those BG divides. That's true.
Yeah.
But the problem is that you see for general BMS, you have essentially you have combinations of many BSCs with different crossover probabilities.
Oh, that's what you're doing. I understand. I see. Mm-hmm.
Yeah, so it's like you need to group up different Ys, and that's,
I understand. Yeah, it's different from what I had in mind, but yeah, I understand. Now, this zero code word assumption that you were discussing in the last part, they may have discussed this in LDPC codes, where they also do bitwise decoding and where they also always rely on this zero code word transmission for the analysis. And so I remember discussions way back in the literature.
I see. Okay.
Because it is clear that this is not an issue at all if we do max likelihood block decoding, right? But for bitwise decoding, this is a bit of an issue, but it's exactly what they have been doing for LDPC codes.
I see.
And a general question, how does this fit in the general scheme of polar codes attaining the scaling?
You mean how does this fit into the main result
Yes.
in the paper?
Yes.
Okay. And by the way, can you still hear me clearly?
Rather, yes. Yes.
Okay. Yeah, I guess it makes sense to give a short explanation. So basically, you see, let's say we have a n by n matrix, random matrix, n by n. And you see, you have, let's say, V1 to Vn, and multiply with this matrix, you get x1 to xn. And then you put it through channel, you get y1 to yn.
Mm-hmm.
And then, by the theorem that we just proved, you will have a threshold somewhere around here, somewhere around n times the channel capacity.
1 minus.
You will have yeah. So basically, after this, below this threshold, you will be able to decode every bit perfectly. The conditional entropy of every bit is, you can view it as 0. Above the threshold, the conditional entropy of every bit is 1. And here you will have some the so-called unpolarized bit, where the conditional entropy is not, you don't really know what that is. And the crucial thing is that our theorem just now implies that the cardinality of this, the number of these unpolarized bits is basically upper bounded by square root of n times log square n.
I see, I understand.
Yeah.
Mm-hmm.
That's a crucial part. So you see, the number of these unpolarized bits, that in polar codes, you know this very well, right? In polar codes, this just determines your gap to capacity.
Yeah, this the gap to capacity or speed of polarization, whatever you call it.
Yeah, so you see, this is just a one kernel. We haven't, in polar codes, you need to repeatedly use this kernel many times. But so you see, in one kernel, this is a number of unpolarized bit. So let's say you recursively use these kernels, and let's just assume, for simplicity, that once the subchannel is polarized, it will never go back to be unpolarized.
Yes.
This assumption is not true, but almost true. Okay, let's assume this. So you see, every time you get this many, let's say you get a square root of n of unpolarized bits. So in what happens in the next step of polarization, where you get square root of n multiplied with square root of n. So each time you get one more step of polarization, you multiply with one more square root of n. So eventually the code length is n raised to t's power. This t is the step of polarization, but unpolarized bits is square root of n raised to the t's power. So you can see that, so you can see that the scaling is really, if this is capital N, the unpolarized bit is more or less square root of capital N, and this is more or less your gap to capacity, very roughly speaking.
This is what we want to accomplish. Yeah, I understand.
Min, I have a question. The strong converse you proved was for a random G, but this is probably true also for most fixed Gs, right? Through some additional argument. Do you think that can be done? In other words, for most, it should be possible to wean out a small set, and then this result is true for most Gs in a certain set.
So that's precisely what we proved.
But that is the statement, right? The concentration.
The concentration state.
It's in the theorem.
Yeah, I thought that's precisely what we proved.
No. You're averaging over G, right? Eventually.
No, look.
The VI, H of VI Y, right? The Y is determined by the distribution of G. I mean, VI is of course.
Look, look, Prakash, this is for a fixed value of G.
Ah, okay, sorry. Yeah. Okay, fine. Sorry. Yeah, it's fine. Good.
Actually, Y does not depend on G, right?
Yeah. Well, Y, the distribution of Y will depend on G initially, but then it shows that it doesn't play a role. So if you start with the V's, then the X's are generated through the V's and the G, and then the Y comes out of the channel. So distribution of Y will depend on the distribution of G, but eventually it doesn't play a role here. That's what
we could discard X G altogether because we say for 0 it is good.
Yeah, right.
Yeah, so basically,
That's right.
if you
that's it. Yeah, that's the one. Yeah.
A bit of a side question, Min, if I may. So let's forget about polar code. So there is this strong converse for bit decoding. What if we allow some type of the rate distortion scenario? So we allow ourselves some loss. Is it possible to make any quantitative statement of that kind for transmitting at rates above capacity?
does this question has anything to do with bitwise?
Yes. Let us say we allow some distortion per bit. I understand it's a foggy question. I'm sorry, but I'm just.
I don't know. I need to think more before properly answer it.
Yes. Same here.
Okay.
So any other questions?
Are you trying to say something?
Not really.
Okay. So I'm actually I was teaching today. So I am teaching every Thursday. Today I talked a lot.
I see. Well, for us it's still ahead of us. It's the beginning of the day.
Well, you taught us very well. So thank you very much.
It's just
thanks indeed. Very clear. Very good talk.
Okay. Thank you.
All right. Thanks.
Thanks, man. Thank you.
Goodbye.
Bye-bye.
Okay. Thank you. Bye.